I'm going to model January 13, SS02, question number 5. This is a question which is a discrete probability distribution question. And the first part of the question, given a probability distribution, the context is different subjects at school each weekday, Monday to Friday, asked me to show that the mean of x is 3.51. I've done that by multiplying the x value by the probability that x equals x for each one. And if I do that 0 times 0.00 plus 1 times 0.03 and so on through, I get 3.51, and I've been able to show there that I've calculated that. Because this is a show that, you make the assumption really that the answer is not given, and you work through as if you have to calculate 3.51, and that's been done there. I'm also asked to calculate the variance of x. Now the variance of x is calculated by calculating the expectation of x, which we've already got, the expectation of x squared, and then plugging it into a formula, and I'll show that in just a moment. So the expectation of x squared is calculated by multiplying the value which is x, squaring it, and multiplying by the probability that x equals x. So it's 0 squared times 0, 1 squared times 0.03, 2 squared times 0.12, 3 squared times 0.34, and so on. That gives me 13.35. I'm then going to use the formula that the variance of x is equal to the expectation of x squared minus the expectation of x all squared. So 13.35 is my expectation of x squared, and I'm going to take from that the expectation of x, which I calculated in the first part, 3.51, and square it, and my answer is 1.0299. In part B of the question, it asked me to use the probability distribution to answer some questions. It asked me, first of all, find the probability on a particular day. Alex is given more than 3 pieces of homework. And it's as simple for this part as saying, well, look, more than 3 is going to be 4 pieces and 5 pieces, and the probability of that occurring 0.33 plus 0.18, which gives me 0.51. For part 2, again, I wouldn't advocate squashing your work up quite as much as I am here, I just want to get it on the one page to show you. For part 2, it says at least the modal number of pieces of homework. Well, just looking through here, the modal number of pieces of homework is 3, because that's the one that I've got the greatest probability attached to. It does ask me here for at least the mode, so it's going to be 3 or greater, so 3, 4 or 5, and I'm going to add those probabilities together. And if I do that, it gives me 0.85, so that's 0.34 plus 0.33 plus 0.18, and that gives me 0.85. The final part here, part 3, says fewer than the median number of pieces of homework. The median would be the value which is at 0.5% through my distribution. Up to this point, I'm 0.03 through the distribution, 0.15, 0.49. So my median value is just going to squeak into this category here, which is 4 pieces of home learning. So fewer than the median value, going to be 3, 2 and 1. And if I add 0.34, 0.12 and 0.03 together, I get 0.49. So just again, that 0.49 has come from the sum of that, that and that. Okay, and that's my answer there, and again, it might be prudent just to underline those. In the second part of the question, it suggests that a Poisson distribution may be a good model for the data, and asked to give one reason apart from a comparison of the values of the mean and the variance found in part A, why a Poisson distribution would not be a suitable model in this context. Well, a Poisson distribution shouldn't have an upper bound, and we're bound here with 5, and in practice there probably would be a significant probability of having more than 5 pieces of home learning per week. So as the Poisson doesn't have an upper limit, this would not match the context of the question. C part 2 reads as follows. It says, Siobhan, another friend of Alex, suggested that the data in the table could be modelled by the binomial distribution with n, 5 and probability 0.7. Explain whether this suggestion is supported by your answer to part A. Well, in part A, we calculated the mean to be 3.51, and we calculated the variance to be 1.0299. If you remember from work before, the expected value or the mean of a binomial distribution is calculated by doing n times p, and 5 times 0.7 is 3.5. If we just cast an eye back here, in the first part we had a mean of 3.51. Those two are very, very similar. Similarly, for the second part, the variance is found by doing n times p multiplied by 1 minus p, and if I do that on a calculator, I get 1.05. And again, comparing with the value that I had before of 1.0299, 1.05 is actually very close again. So, asked whether or not this suggestion is supported by your answer in part A, I would suggest yes, absolutely. It does seem that the binomial is providing a very good model, as these are very, very close to the calculated values.